Hey everybody, Dr. A here, and in this video we are going to be explaining some background information on the one-dimensional, which we abbreviate 1D, laboratory consolidation test in soil mechanics. So this was developed by Terzaghi in 1925, and it uses a device that we call a consolidometer, which could also be called an odometer. I personally often call it a consolidometer. And the way it works is that we apply a vertical load to an undisturbed soil sample that comes from a Shelby tube. So you're going to get an undisturbed or Shelby tube sample, trim it down to a small cylindrical shape, very carefully, of course, to maintain its level of undisturbedness. And then you're going to plot deformation versus time. So you're applying a vertical load to the specimen, and when you apply that vertical load, the specimen is going to compress, it's going to deform, and it's going to do that over time. And when you make a plot of the deformation versus time, you're typically going to express the time on the horizontal axis on a log scale. Now, you want to do this for several increasing loads, and then you want to do it for a couple of decreasing loads. So what that means is you're going to start at some initial loading, and you're going to generate and produce data of deformation versus time, and then after about 24 hours, you're going to increase the load, and you're going to do it again. You're going to develop more data for another 24 hours of deformation versus time, and you're going to do that several days in a row. So if you notice, I wrote a sentence here: each deformation versus time plot will take about 24 hours worth of data. And so every day you're going to come back and you're going to increase that vertical load a bit more, and you're going to generate more data that shows deformation versus time. You're going to do that several times. Then for a couple of days, you're going to decrease the load. You're going to relieve the load, and do that for a couple of days. And so I'm going to show some sketches of deformation versus time plots in just a second in this video. But before we do that, I want us to visualize the side view of a consolidation testing apparatus. So this is going to be a side view or a profile view of what a simple consolidation test would look like. So I'm going to say profile view. Now let me tell you what we're looking at. This is kind of looking at the side and through a cross section. So this shaded area right here, this is a container that will be filled with water. You see we have a water line here, and inside of this container that is filled with water, we're going to have our soil specimen. So this is our cylindrical soil specimen that was trimmed from a Shelby tube, and it's going to be encased inside of a metal ring. So we see the sides of this metal ring that it's encased in on either side of it. And then on the top and the bottom of the soil specimen, we're going to have porous stones. So again, this is a small tabletop apparatus, and this is kind of like a cross section or a profile view, a profile cross section view of that apparatus. Okay, and again, the whole thing is saturated. And here at the top, we're going to apply that vertical load. I showed it as a stress because even though it's a force that's being applied here, it's going to spread out as a stress across the specimen. And then here you're going to have a dial gauge mounted up that's actually measuring the deformations. Okay, so again, this is just meant to give you a nice visual representation. If you have a textbook handy, a soil mechanics or a geotechnical engineering textbook, and you look in the consolidation chapter, that any textbook in soil mechanics or geotechnical engineering will probably have a figure that looks kind of like this, but obviously it'll be drawn a lot nicer than my freehand drawing, and you may even have a photo or two of an actual tabletop apparatus that depicts this setup. So let's figure out what we mean by these time deformation plots. Okay, so let's say you start the test day one. Okay, day one, we're going to say start of test. Okay, now on day one, you are going to apply your first load. Okay, so apply load 1 as sigma 1. So it'll be a stress applied to the top of the specimen, just kind of like I drew here, okay? An effective stress is what we're calling it, all right? And what's going to happen is you're going to keep this load on that specimen for 24 hours, okay? So we're going to say sustain load for 24 hours and measure specimen deformation, and it'll be a compressive axial deformation with time. And then what you're going to do is you're going to take this data and you are going to generate your deformation versus time plot, okay? So an example of deformation versus time plots would look something like this. Here's deformation on the vertical axis, and here is time on the horizontal axis, and usually time is going to be expressed on a log scale, and this is going to show a deformation in downwards or compressive direction. And when you plot this data, it's going to generate a curve over time that's going to have this kind of shape. So you're going to have several of these data points, more than this, but several data points that you have collected, and you're going to connect these data points with a smooth curve, okay? And that's your first deformation versus time plot. Now, this initial region of the plot above the approximately linear portion is going to be your initial compression region, okay? And then this bottom region where it becomes very nonlinear again is going to be your, below which is going to be your secondary consolidation region. And then in between here is your primary consolidation, or where most of your primary consolidation is occurring, okay? So that's day one. And then what you do is you come back 24 hours later, so now it's going to be day two, and you apply a larger vertical load to the same specimen. And we're going to call that sigma 2, okay? And you let this sit for 24 hours, and you generate the same kind of plot. Okay, here's deformation in a compressive sense. Here's time on a log scale. And again, you're going to get another similarly shaped plot. And you do this for several days, okay? So we're going to continue for several days. Usually this is, 4 to 6 days, okay? And then after that, after your last day of increasing the load, you're incrementally increasing. Sigma 2 is bigger than sigma 1, sigma 3 is bigger than sigma 2, so on and so forth. You will have a few days, 2 or 3 days, where you are gradually decreasing the load. So then we're going to say end with 2 or 3 days of decreasing sigma, okay? So in total, this entire process on the same single specimen could take you anywhere between 6 and 8 days. So you'll have, 4, 5, 6 days of increasing the applied load on the specimen, and then you'll have 2 or 3 days of decreasing the applied load on the specimen, okay? Now, what happens with that? So at this point, you're going to have a collection of several of these deformation versus time plots. So I'm going to say now we're going to use information from each of the deformation versus time plots to generate one plot of void ratio, which you remember we call that E, versus effective stress, which we're going to call that sigma prime, okay? And we're going to plot sigma prime on a log scale. So how do we develop this one plot of void ratio versus effective stress? Well, here's the few steps that we take to do that. So to generate void ratio versus effective stress, the first thing we're going to do is we're going to compute the height of soil solids, okay? And we're going to do that by saying the height of the soil solids is equal to the weight of the soil solids divided by the cross-section area of the specimen times the specific gravity of the soil specimen times the unit weight of water, okay? So make a note here, this W sub S is weight of soil solids, and A is cross-section area of specimen, which is usually a circle because it was cut from a Shelby tube, okay? So then step 2, we're going to compute the height of voids, okay? And the way we're going to do that is we're going to say the height of the voids is equal to the total height of the specimen, the total original height of the specimen, minus the height of the soil solids, that H sub S value that we just calculated in step 1. So again, regular H is the initial height of the specimen. Specimen initial height. All right. And then step 3, we're going to compute the initial void ratio E naught. Okay, so E naught, if you remember the basic definition of void ratio, it's volume of voids over volume of solids. Now, we can rewrite this as the height of voids times the cross-section area divided by the height of solids, also times the cross-section area. And it's the same specimen that's inside of this ring, right? So if we scroll all the way back up, the cross-section area is given by this plane right here that's inside. It's encased in a ring. So the cross-section area is staying the same, okay? So we can cancel the cross-section area. And we'll make a note here. We're going to say A remains constant since the ring prevents a Poisson effect from occurring. So hopefully you remember from mechanics of materials, a Poisson effect is an effect on a specimen. Whenever you load on put a load on a specimen in one direction, it'll deform in one direction, and then it will simultaneously deform in the opposite sense in the perpendicular direction. So if you compress a specimen, it will shorten in height, but its lateral dimension will bulge. Well, this will not happen because the specimen is within a ring. It's usually some kind of metal final ring. So a Poisson effect will not happen. Thus, we can cancel the areas here, and we can calculate the initial void ratio as the height of voids over the height of solids, okay? Now, step 4, we're going to compute the change in void ratio for load 1, okay? The way we compute that is delta E1 equals delta H1 divided by H sub S, okay? Now let's talk about this delta H1, okay? That's a new little calculation in our process. Delta H1 is obtained from the initial and final dial readings for load 1. Okay, so for the first load increment, that's sigma 1, delta H1 is the difference between the initial and final dial readings. So basically, if we go back to day 1, load 1, it's the difference between the initial and the final dial readings from load 1, which happened on day 1, okay? And then we say the change in void ratio is that value, delta H1, over the height of the solids. And then step 5, we're going to say compute the new void ratio, and that's going to be E1, and that's E naught minus delta E1, okay? Now, from here, you're going to repeat this process for each of your loading stages, or each day of loading that you have. So I'm going to write in green here, repeat steps, and specifically, it's going to be repeating starting with step 3, but we're going to repeat steps for each day of loading, okay? And so finally, we will create a plot of void ratio versus effective stress. And so when we make our void ratio versus effective stress plot, it's going to look a lot like this. Here is void ratio, E. Here is effective stress on a log scale. And the plot is going to look something like this. You're going to have several days of loading, and then you're going to have a couple of days of unloading. So these days here, these data right here, these 5 data points, that's your loading data. That's when we were increasing the load from sigma 1 to sigma 2 to sigma 3. And then the last couple of days where we decreased the load, we generated these 2 data points. So basically what's happening is you're generating a plot that looks a lot like this. This is nonlinear, and it does something like this, okay? And we're going to make a note here. We're going to say these points right here are the loading days, from the loading days, and then these 2 points here are from the unloading days, okay? We sometimes call this part of the curve the rebound curve, okay? Now, you might be wondering, what is the purpose of this? Why do we care about this? Well, from this plot, we're going to say from the E versus sigma prime plot, we can determine several consolidation properties used to compute the primary consolidation settlement of a soil in the field. Okay, so what are those properties? Well, from here we can determine the pre-consolidation pressure, which is sigma prime C. We can determine the compression index, which is C sub C, and we can determine the swell index, which is C sub S. Now, in my follow-up video, I'm going to discuss how we can determine each of these important properties from this kind of plot. Okay, so that's going to be our very next video. If you found this video helpful in your understanding of the primary consolidation laboratory testing process, please hit like and subscribe and be on the lookout for more useful videos like this. Thanks for watching.